Yeah, welcome back again from my smallish home office. In the last term, I've already completed the course DECA 1, and I hope you had a chance to watch it because this course that I'm talking about this term, Designing Code Analysis for Large-Scale Software Systems 2, DECA 2, it's really a follow-up course. And so you will be again, having all the necessary material online on YouTube. If you are interested in following up on some of the exercises, feel free to email me in private and we can probably also share some with you. To get you started with the second course, I first want to give a brief introduction, of course. I'll briefly reintroduce our group and what we're doing. I'll then also briefly again recap DECA 1, what we did there, just to bring you up to speed again. I'll outline what's coming up in this course, and then I'll also give some administrative information that's mostly relevant to people at the university. Then also in this first week, I want to talk about one first actual topic, which is called sparse IFDS, but more on this later. So first of all, about our group. So I'm running the Secure Software Engineering Research Group, so we are concerned with aiding software developers in helping them, make their software that they develop more secure. And we are developing a number of popular tools, and as you can see here, many of them, they have been focused around this suit framework, but another framework that we are now heavily invested in is also called Phaser for the analysis of C and C++ programs. So if you have participated in our labs in the last term, you've already seen both of these tools. And these tools are pretty popular, so they're being accessed from all over the world, and they are still gaining in popularity, I would say, every week. Both Suite and also Phaser you can access online, so they're both free open source projects that we also do not necessarily want to run entirely on our own. So we are currently maintaining them, but you are very welcome to contribute and extend them, at the very least file bug reports, but also maybe fix bugs or contribute features, both for Suite and Phaser. Help is always very much appreciated. It's a lot of work actually to maintain these tools. Luckily, we also have the ability to collaborate with lots of partner companies in this space. So there are a number of companies now using static code analysis and building on top of them, some of them even building their own tools. And my research group, like you probably already know, it's not only spanning the university, but also Fraunhofer IEM, where I have my own division. And there we are particularly engaged in strong collaborations with these companies, usually already financed also by these companies. And we're helping them roll out particular tools, develop dedicated static analysis tools for their purposes. And that's also where we gain a lot of insights because, well, many of the algorithms that are published in the literature, some of them which we published ourselves, they seemed good at the time and they worked well during lab experiments. But then when you roll them out and try them again on some other real world applications that maybe you hadn't tried before, or try to just deploy it on a really large scale, then you hit challenges that you have never anticipated. And that brings us back to the whiteboard, where we think about other data structures and algorithms and how to improve things. Also, turns out that there are many engineering challenges, problems that are maybe not conceptually that hard to deal with, but that need to be dealt with nonetheless. And these are also topics that I want to cover in this course, DECA 2 in particular. So that will be one aspect of this course, telling you more about how to make things truly practical in an industrial setting. Normally, when you want to find us and we're not all in home office like we are still this year, unfortunately, then you can find us in these two buildings. So this is where my university lab is situated. This is where Fraunhofer is situated. So hopefully, I don't know, by summer or fall at the latest, you will be finding us there again on a regular basis. So in general, my group is concerned with many topics in the realm of secure software engineering. So it's a lot broader than static code analysis. So we also care, for instance, about usable security, security in type systems, but also usable cryptography. We have done works on risk assessment, threat modeling, this kind of stuff. But static code analysis is a major centerpiece of our research. And that's also why I'm dedicating even 2 courses to this topic. So with that, I want to briefly recap what I have covered in DECA 1 already, so that you can see how it connects to DECA 2 and what we will cover in DECA 2 in addition to that. So in DECA 1, which is a prerequisite for this course, we already taught you basic algorithms to conduct efficient inter-procedural data flow analysis, right? So we started with intra-procedural analysis. We even discussed flow insensitive algorithms, and type systems, and so on. But in the end, we talked a lot about distributive frameworks such as IFDS and IDE, but also frameworks that are non-distributive, such as Vasco. That's what DECA 1 was mostly about, right? And I discussed which of these algorithmic frameworks is most suitable under which circumstances, so that you can really make a well-informed choice the next time you are building your particular own static analysis. Then you will know what algorithm to choose, which data structures to use. Yet there are other powerful advanced concepts, right? So these concepts will really be hard to understand without DECA 1. So I won't be able to repeat everything that we did in DECA 1 when I'm teaching the subjects of this course here now. But I also won't have to, because all the material of DECA 1 is still available. You can even watch it on YouTube. So whenever you have a particular question on a particular subject, feel free to skip back there and take a look at what I taught there. In DECA 2, I will focus on 2 things, like you will see in a minute. So we will cover more, let's say, rather theoretical concepts and frameworks, but I also will explain important practical aspects that I was unable to cover in DECA 1 due to just time constraints. So I really want to tell you what, in addition to these algorithmic frameworks, it takes to make program analysis really work in the real world. And I also will explain to you some real world program analysis tools that actually have been used in practice and are even being used in an industrial setting these days. And I will explain to you how we got there and which of these algorithmic tricks exactly we use to make that happen. So the outline of DECA 2 will thus be as follows. It will basically be in 2 parts. So the first part will still strongly connect to what I explained in DECA 1. So it will connect to these conceptual analysis frameworks. So in particular, in DECA 1, we explained IFDS and IDE, which were particular instances of the functional approach. And I will start off by explaining 2 extensions to these. So in this week, I will still be covering sparse IFDS, which is extension of IFDS that makes it more efficient. Then the week after, I will be talking about SPL lift. So SPL here stands for software product lines. And SPL lift is basically an extension of the IDE framework that allows you to analyze a large number of multiple variants of the same program. So you could also say a software product line entirely at once. And we published this a few years ago. And I think it has some very interesting algorithmic properties. That's why I'm presenting it here. Um, then another concept I want to talk about are so-called pushdown systems and weighted pushdown systems. So pushdown systems are very clever and reduced representation. It's a very nice computational model that can be used to represent distributive problems. And in particular, pushdown systems, they more or less mirror what you can do with IFDS. And weighted pushdown systems, they more or less mirror what you can do with IDE. So if you remember from DECA 1, IDE was adding to IFDS certain edge functions that can execute additional computations. And here in these weighted pushdown systems, these edge functions are basically represented by so-called weights. So it's a similar concept, differently expressed. Um, but we use both of these mechanisms now heavily in our work, and that's why I think it's also worthwhile explaining them here. Another unrelated but also very important concept these days are so-called demand-driven analyses. So far I have explained program analysis that are either intra-procedural, so they only look at a single procedure, or they actually cover the entire program, right? So it's a whole program analysis. But demand-driven analysis, they are somewhat in between. So in particular, a demand-driven analysis, by definition, it will not start at the beginning of your program. So won't start at your main method, so to say, right? But it will rather typically start somewhere in the middle of the program where there's a particular interest, a particular demand for the analysis. So for instance, let's say you want to identify misuses of cryptographic APIs, as we've done in the past. Then it might make a lot of sense to identify calls to these APIs in the first place, and then do a very targeted demand-driven analysis of the code that surrounds these particular method calls. And that's actually exactly what we're doing, and that's exactly one context where such demand-driven analysis are important and interesting. And I will explain to you how we implemented demand-driven analysis or the concept of these analyses in general, and then how we applied this to the concept of push-down systems yielding so-called synchronized push-down systems. So that's a very recent work that we published using a tool called Boomerang that came out of this. So Boomerang gives you a demand-driven pointer analysis based on synchronized push-down systems, actually. And then again, we use this to build a real-world bug finding tool, which is called CogniCrypt. So that's a freely available open source tool that actually uses all of these concepts here to let you very easily identify misuses of crypto APIs in real-world programs. That covers the first part of this course. So you will see there's still a lot of new concepts in here, which is why for the university students, this will also be accompanied by pen and paper exercises that will help you optimally prepare for the final exam that will also cover lots of these topics here. Then in the second part, we'll be talking much more about practical analysis tools. And here, one tool that we were talking about is FlowDroid. So FlowDroid is already a few years old, but it was developed in our group, and it's still the state-of-the-art static analysis tool if you want to do Android chained analysis, which is a topic that still many people are interested in. In particular, it uses IFDS to do its computation, but it also has a particular way of constructing useful call graphs for Android, and those are two topics that I want to talk about. Then another interesting topic or challenging topic also when you're doing static code analysis is that you need to create call graphs that are correct also for applications that use reflection. And so reflection is a way of calling methods indirectly in Java. So for instance, you just provide the name of a method or the name of a class. And yeah, there are certain tools that help you deal with this. For instance, one is called Tamiflex and one is called Judge. And we'll be discussing these in the course as well. Um, then we want to generalize these concepts because in general it can make sense to construct call graphs using a so-called hybrid analysis. So by using static and dynamic analysis. And there are a couple of approaches also in this space that we developed in the past. One is called Harvester and one is called Heapster. And these we will also be covering in the course. And then another topic that I want to talk about is about customizing static analysis, because in particular, when you talk about static security code analysis, then many of the properties that these tools need to check, they are really specific to certain frameworks and libraries that people are using. So for instance, an authentication library, right? Um, and in order to make the analysis find anything useful, right, in order to make them detect actual vulnerabilities, they need to be customized. So you need to tell the analysis, for instance, what is the source of a taint analysis? Or what is a sink? What is a sanitizer? What is a certain authentication method? And there are several approaches that help you deal with this. One is a language-based approach called FluentTQL. One is a machine learning-based approach, so active learning-based approach that's called Swan Assist. We want to cover both of these in our course. Um, and then in the end, I also want to talk a bit more about improved user experience and even gamification. So that's also an increasingly relevant topic. So by now the community has accepted that it's not good enough to just give them a random, command line tool that has weird configuration options and then maybe spits out error messages in some language text file format. People won't really use that in practice. You also need concepts to actually display error messages very well to users, maybe in a CI/CD pipeline or even in an integrated development environment. And you also might need to help them prioritize the work that they do. And there are several concepts here, for instance, just-in-time analysis that we worked on, or also rule graphs. And I want to explain at least some of these in the course. I won't be able to cover all of this research because there's an increasing number of papers in this space. But at least I want to give you the gist of what's happening there. Yeah, and you might have noticed that I've put some of these tools in boldface. So these are the tools that we will likely be using in labs that will be accompanying this course. So if you are a student participating in this course, then in the second half of the course, we will have some hands-on labs where we will be explaining some of these tools and letting you get some first-hand experience with them. And it will likely be the ones that I've put in boldface here. Okay, that concludes my summary of DECA 1 and what will be happening in DECA 2. So I hope you find this interesting and you will follow throughout the rest of the course. In the next video, I will still be giving you a little bit of administrative information that will be relevant mostly for university students. See you then.